Okay, so I will present verifying outsourced object detection, outsourced computation in an edge computing marketplace. So this was a paper authored by me and Gonzalo, Munilla, Garrido, who is not present today. So first of all, let's get into the motivation of an edge computing marketplace. So basically, an edge computing marketplace is a collection of nodes that try to outsource computation and other nodes who are willing to offer computation for a service fee. And basically, the marketplace matches third-party resources to computation demands. And to better illustrate it, we can see the following scenario on the left, that if we have a closed ecosystem with fixed host assignments, then IoT devices might not get optimal service in terms of latency and availability of edge servers. But if they could actually use also third-party resources in proximity, then they could have increased connectivity. It leads to more competition between edge servers, and so this also increases responsiveness of the applications and allows IoT devices to utilize their, allows edge servers to utilize their unused resources to accept more computation offers. And so the general problem statement when you move from a fixed host assignment where IoT devices typically trust their edge server where they outsource their computation to a dynamic resource matching with untrusted participants is that you have to account for malicious participants. So for example, when an IoT device outsources computation to a contractor, so any arbitrary edge server, then actually the edge server does not have an incentive to give back a correct result unless there's some kinds of reward and penalty mechanism in place and a verification scheme in place such that the IoT device can actually verify that the computed result is correct. And in order to tackle this problem, most related work and also our work uses a third-party verifier to verify results sent back by the contractor to the outsourcer, and then basically the outsourcer can check if both responses are equal. However, this solution in itself is not sufficient. This is just a basic setup how you can approach this problem, because more specifically what can go wrong is so not only can an individual contractor cheat and give back a false result, but also if you have a third-party verifier which is also untrusted and verifies the results, then there can be collusion between participants. So for example, the verifier and the contractor that can collude to trick the outsourcer in believing a false result. At first we identified different challenges that can happen in this scenario. And at the end, we identified 11 different threats in total. And these threats can be categorized into malicious behavior by an individual. So that would be, for example, if the outsourcer refuses to pay after a contract, or if the contractor sends back a false result, or if the verifier sends back a false result. Then malicious behavior by collusion. So if any two parties collude against a third party to either refuse payment or send back false results. And then also we have quality of service violations. So that would be if a node doesn't have the necessary service parameters. So for example, it acts in high latency and cannot offer real-time service. Our research objective was to design a verification scheme that first of all performs in real time, then is secure against all identified threats, and it should involve a minimum number of trusted third party in the whole system. To come to the literature review, so basically edge computing marketplaces offer different research perspectives. So not only can you design a verification scheme for it, but you also have to think about resource matching. So how to even match the resources, the computation resources to the computation demands and so on. Then within the verification scheme, there can be different operations of interest. And in our case, we looked at arbitrary functions. So we want to be able to verify any kind of computation. And later we stress test our verification scheme with object detection using convolutional neural networks. So that's why these two types of operations are of interest in our case. And there has been quite a bunch of related work to both operations. Then there are multiple available verification approaches, and we choose re-execution. That's the basic approach that we showed before, that you have a third-party verifier that re-executes some of the inputs, and then the outsourcer has to compare the inputs. And then there's also a distinction between complete re-execution, where you re-execute every, and sampling-based re-execution, where you only statistically check some inputs and basically get a sufficient confidence to detect a cheating attempt, but save computational resources. Lastly, here are our the techniques that related work usually uses to tackle the different identified challenges. And we found that two challenges can currently not be solved by combining the identified resources by related work. And so basically what we just did is we combined the techniques presented already introduced by related work, and we added a few new techniques so that at the end we can actually solve all the identified challenges that we found. And basically to explain the verification scheme, so first of all, in the initial situation, we assume that there is an outsourcer that wants to outsource computation and a contractor that offers computation for a fee. And then in the initial situation, we have a bunch of available verifiers that are now able to assist in this contract and basically verify, so re-execute the computation on the sample of inputs. And now the risk when selecting a verifier is that there might be both collusion between outsourcers, between the outsourcer and the verifier, meaning that the verifier responds back that every result of the contractor is false, and then the outsourcer and the verifier can basically deny payment to the contractor, but also there might be collusion between the contractor and the verifier such that they trick the outsourcer in believing a false result. And the first technique we use to prevent this threat is called randomization, and this is happening prior to any outsourcing. So this is still just selecting a verifier before the actual outsourcing starts. So we call this the preparation phase. And in the preparation phase, basically the outsourcer and the contractor commit both to a random number, but this random number is not revealed to the contractor. And thus both parties basically have verifiable proof that they selected a specific verifier, but the contractor doesn't find out to which verifier both parties committed. So it can't easily contact the verifier to engage in planned collusion. And then there's also a risk of what we call ad hoc collusion. So even though if the contractor and the verifier do not know each other, there might be a statistically favorable response that is correct with a high probability. For example, in case of object detection, just giving back the result that no object is present in the current frame is actually quite a lazy strategy that can be successful with high probability. And so you also want to avoid that there is this ad hoc collusion, that even though parties do not know each other, they choose the same lazy response. And basically, to solve this threat, you can introduce game theoretic incentives, and that's already shown by related work that it works quite nicely if you introduce also fines for each participant when caught cheating, and a bounty for the other participant if they find the first participant cheating. Then you can basically circumvent this behavior that if the adversaries are rational payoff maximizers, that they would always choose to act honestly and basically try to convict the other party of cheating instead of trying to respond with a false response. And so basically these are our two strategies to deal with collusion. And then after this preparation phase is finished, we can start the actual outsourcing. And during the actual outsourcing, we use sampling-based re-execution. So that's what I referred to earlier, that the verifier only verifies samples in periodic intervals. And then the outsourcer needs to check if basically two responses belonging to the same input match of verifier and contractor. And actually we can show that if we if the contract goes on for a while and we collect a lot of inputs, that with a very low sampling rate, we can actually have nearly 100% confidence of catching a malicious contractor. So basically, sampling-based re-execution has a lot of computational advantages, but only a slight trade-off in security. And also we use digital signature and acknowledgement with each input. So meaning that with each input, the outsourcer acknowledges how many frames or inputs the other respective party has processed. And this confirmation is signed, and also each response by the other party is also signed. So whenever the contractor gives back a result to the outsourcer, the result is signed, and these signatures act as a proof that later any party can go to what we call payment settlement entity and basically show the signatures it's collected and redeem payment. And also when a response is false, then the outsourcer can basically present the original input and the signature of the contractor, for example, of having received the false result, and then successfully convict another party of cheating. And so that's happening in the last phase we call closing phase. So there's a payment settlement entity that checks the signatures of the last message and determines whether everything was done correctly, and then transfers the reward. And in a deadline, basically any party can contest this decision and submit a proof of malicious behavior. And the advantage of only sending signatures during the execution phase and using this payment settlement entity as a trusted party at the very end is that the payment settlement entity actually does not have to be located at the edge, but can be contacted later with an arbitrary delay, and basically does not end up the bottleneck of the system. And also it's easier to find a trusted party in a non-edge context than to find a trusted party at the edge. And so there, in the malicious case, we also want to prevent the payment settlement entity from actually re-executing the function, because it might not have the necessary resources or also the necessary application to do so. So we also designed a protocol called contestation, where each party can basically convict another party of cheating by re-outsourcing the current job to 2 additional verifiers, and then basically shifting the random verifier support of their response. And basically at the end of the process, whichever party has the majority of random verifier support is believed to be honest. And this variation shifts more load from the payment settlement entity to ensure that it doesn't become the bottleneck of the system, such that only edge nodes actually do any kind of computation, and that the load is distributed among all the participants in the system. So just a quick high-level overview again. So we had the preparation phase to basically prevent ad hoc and planned collusion. Then we have the execution phase where the actual outsourcing is happening and participants send signatures and acknowledgement to each other. And these signatures at the end can be used to contact the payment settlement entity, which is a trusted party not present at the edge, but anywhere, and that can act in arbitrary delay. And this entity can be contacted to redeem payment, and also within a deadline after a participant issues a payment request, any other participant can contest and use our contestation protocol to basically convict another party of cheating. Then we implemented the scheme using 3 nodes in the local network. And basically we used, as I said, object detection with pre-trained convolutional neural networks. So we use this kind of use case because, for example, for CCTVs, it has a high relevance in edge scenarios to do object detection, and also it's a quite complex use case to stress test the verification scheme. And here you can see basically the different parties. They all communicate in the local network via TCP sockets, and basically the outsourcer always captures new frames via its video camera, then sends the frames over to the contractor. The contractor is sending back the bounding boxes with the pre-trained CNN, and the verifier basically does the same on samples, and then the outsourcer compares the responses. And so the hardware we used is we used a Raspberry Pi connected to a camera to capture the video, and then we used mid-range hardware for contractor and verifier, and also we used low-end hardware with an edge accelerator. So edge accelerators are tiny devices that you can use at the edge to very efficiently do a specific kind of operations. In our case, it was CNN inference. And so we used a Coral USB accelerator that can do inference quite efficiently. And to show a quick demo, you can basically see in the top, you can see the contractor that is basically performing the application with very high frame rate. So basically responding the bounding boxes with the bounding boxes in real time. And then below, there's the verifier that basically verifies the application with very low frame rate. And you might have seen that the lower video X was basically at a much lower frame rate, because the verifier only has to check statistically if the so that the outsourcer can decide whether the responses are equal. And so the key results of the benchmark was that with different models, so we used YOLO version 4 Tiny and MobileNet SSD version 2. And basically the outsourcer can achieve very high frame rates. So in one case over 200 FPS, in the other case over 140 FPS. And also the contractor was able to achieve more than 30 FPS, which was our limit for real time to assess whether it's still possible to do the verification scheme and the task in real time. And also the task actually spent on the verification scheme per frame was quite low, and we further did employed some multi-threading to basically reduce the overhead to zero, because while the GPU is busy running object detection, the CPU can actually handle the task of the verification scheme, and that worked without a problem. So as a summary, basically our verification scheme achieved practicality for even complex use cases. So in our case, the outsourced object detection, and introduced a latency overhead of smaller than 1 millisecond per participant per frame. We solved the identified protocols violations, and we rely on one trusted third party, but this trusted third party does not have to be located at the edge and is only involved in trivial computation and checks. And also you can find a link below to our GitHub repository where the code base is located. And that's it from my side. So thanks for listening.